welcome back to the end of day 3. How is
Woo.
everybody doing out there? Let us know in the comments. I am joined again by Natasha. We have an exciting speaker again with us today to talk more about some really cool things happening in space exploration. How is everybody doing with orbital mechanics? I know that was one of my favorite classes back in undergrad. What about you, Natasha?
Yeah, it was an interesting class. I remember not getting understanding beforehand how this all works and then just the equations. It's really kind of beautiful how the math works out. It's a great subject and I'm excited to learn more from our expert speaker today.
All right. So is anybody commenting about how their
We
day is
always got
going?
Clifford. We can always rely on Clifford to comment. So I think earlier he was pretty tired, but now he's doing good.
That's right. Awesome. Well, I am really excited, especially for this guest speaker. Oh, we got more good. That's all y'all have. So I was inspired. I don't know if you know this, Natasha,
What's
but
that?
my entry into space exploration, and when I first decided I wanted to go to space, I wanted to be an astronaut, but I settled for an aerospace engineer. Um, was that I saw a mission go to Mars. I saw a rover go to Mars. It was in 1997, and I got to see the Pathfinder land there. And we get to hear more about some really exciting missions and somebody who actually worked on all of the rovers who landed on Mars. So while we are waiting for some more comments to come in, I want to introduce our speaker and go ahead and get started. So without further ado, I'm excited to introduce today's speaker, Todd Barber, who will discuss aerodynamics or astrodynamics and mission planning. Todd Barber was working at JPL for just over 3 decades, his first job and his dream job in one. After being introduced to planetary science with a 7-year stint on the Galileo mission to Jupiter, Todd worked for over 20 years on the Cassini mission to Saturn, most of them as propulsion lead engineer. Mr. Barber has focused almost exclusively on propulsion mission operations across a myriad of missions, including Deep Space One, Deep Impact, Stardust, Dawn, SMAP, and most recently, Voyager. He's also answered the allure of Mars by flying Spirit, Opportunity, Curiosity, and now Perseverance to the Red Planet. So, everybody, join me in welcoming Todd Barber. Hello.
Hi, Claire and Natasha. Voice check. How do you read?
Sounds great. So glad you're
5 by 5.
here.
Great. Well, I'm delighted to be back, and I welcome all our students from around the world. I'm tickled tonight to talk a little bit about some ways we really do things at NASA that ties right into your missions as far as orbital mechanics and remote sensing. And just really happy to be back. So we've got a full slide set to go through. I'll be happy to take questions and answers and leave time for that towards the end today. But thank
Great.
you for the introduction, Claire.
Absolutely. Well, let us know in the comments as we watch his presentation. If you have questions, we will ask those after the presentation. I'm going to go ahead and share, and I will be off screen, but I can hear you, so you can tell me when you want me to go to the next slide.
Perfect. Thanks, Claire.
Okay.
That'll work just great. Okay, so this is my title slide, and a lot of it is Voyager material, but also Mars, of course, because I've had the pleasure of working at JPL for 32 years this month, and almost exclusively flying these things. Other geniuses like to build and design the missions like you're doing with space teams, but I like the privilege of actually getting to the launch pad and flying them around the solar system. So we'll talk a bit about how we do that today. So next slide, please, Claire. Okay, so let's start with the rovers because it's kind of the easiest orbital mechanics problem to talk about. And I didn't end up, unfortunately, working on Sojourner, even though I was at JPL at the time. I was so busy with Galileo and getting Cassini ready to launch to Saturn in 1997. But we have a family portrait there. We bring them together at JPL on our front steps in front of the director's building. So you can see full scale and the relative size of the rovers with respect to one another. So Sojourner was a cute little rover on the Mars Pathfinder mission, 1997. about the size of a child's wagon or a microwave oven. And then my first Mars missions then were Spirit and Opportunity, the two twins, in 2003, which landed January of 2004. And those are about now the size of a golf cart or so. Pathfinder Sojourner was named after the abolitionist Sojourner Truth here in the United States. And it was supposed to last the whole mission 1 month. It actually lasted 3 months in total. The rover could not communicate straight to Earth, though. It had to talk to the landed part of the mission, basically like its mother. And I usually don't tell little kids this, it's a little too sad, but the lander died before the rover did. So when that happens, the rover actually drove back to the lander and circled it. Mama, can you hear me? And of course it couldn't hear. It's so sad, but robots don't have feelings. It's okay. It lasted 3 months into its 1 month mission. Spirit and Opportunity, the twins on the left there, were slated for a 90 Sol mission. SOL is a Martian day, and a Martian day is about 24 hours and 39 minutes, a little longer than an Earth day. So it's about 92 Earth days, 3 months basically. So Spirit lasted 6 years to its 3 month mission on Mars. Opportunity went 14 and a half years into its 3 month mission on Mars. So they survived way longer than we ever could have dreamt or hoped for, exploring the red planet. We didn't think, for example, we could survive the Martian winters. Mars has seasons like the Earth. They're a little more severe. It's slightly more tilted, 25-degree tilt versus it's 23 and a half. But the Martian year is twice as long as Earth's year. So on Mars, you have 6 months of summer, 6 months of autumn, 6 months of winter, 6 months of spring. And a clever genius figured out with these solar-powered rovers there, Spirit and Opportunity, hey, if we drive up side of a hill and tilt the solar array towards the sun and then kind of hunker down for the winter, maybe we'll just survive. So we did that for 3 winters on Spirit and about 7 winters on Opportunity. Unbelievable. Finally, we move on to the bigger rovers, and this was the Rover Curiosity, part of Mars Science Laboratory, or MSL, on the right side. Now that's a big vehicle, bigger than a Humvee, and just a huge, huge rover. And Perseverance, by the way, which launched in 2020, landed in February of 2021, is the same size. And it also brought a cute little passenger, the Ingenuity helicopter, which has flown about 34 times on Mars, a design life for about 5 flights over a month. And it's a year and a half later, and we're still flying Ingenuity and driving Perseverance. So that's been amazing. One thing I like to point out on this slide, look at the big wheels there on Curiosity. And there's holes in those wheels. The idea is we would love to drive these rovers like a video game on Mars. Unfortunately, we can't do that because of that pesky Albert Einstein and the speed of light delay, 186,000 miles per second or 300,000 kilometers per second. It's the law. And if you all let us know, we'll hire you tomorrow because we'd love to go faster than the speed of light. Mars and Earth have very different relative positions depending on the time of year of the Martian year and the Earth year. But the minimum distance is about 4 minutes away, moving at the speed of light. You know, the moon is only 1.5 seconds. Mars is the closest it ever gets to Earth. It's about 4 minutes away, up to about 24 minutes. So imagine a video game where you jiggle your joystick and you got to wait 8 minutes to 48 minutes round trip, right, to see what happened with the rover driving the rover. Because of that, we want to program smarts into the rover. And they tend to get stuck in the Martian sand. So someone had a genius idea. Let's drill holes in the wheels. And then as the rover drives across the sand for a 20-inch diameter wheel, 20 times pi inches, about 65 inches, those hole marks will repeat itself in the Martian sand. The rover can take pictures of that, analyze the distance between the holes, and figure out if it's 20 pi inches, great, life is beautiful. Keep driving, full speed ahead, which, by the way, is about 2 inches per second, about like a fast snail. Are we there yet? Are we there yet? Oh, it's so excruciatingly slow. But what if it's only going 10 pi inches? What's happening? Well, it means your wheels are slipping 50% in the sand, and you might bury the wheels in the sand. We don't want that. So the rover is smart enough to hunker down and stop and say, hey, I'm in trouble, Earth, I'm slipping. Now, on a seemingly unrelated topic, we love this rover at JPL. We tricked it out with JPL bumper stickers and getting ready to launch, and NASA said, take those tacky JPL bumper stickers off, and they're like, right, where are our manners? This is a NASA mission. Let's put some NASA meatball stickers on it too. And NASA said, no meatballs, no JPL, keep it classy. So we grumbled a little, but we launched, we landed, we started driving around Mars, and then someone at NASA headquarters, pretty smart cookie, looked down and realized those weren't random holes at all in the wheels. They actually spell out JPL in Morse code. So not that we're full of ourselves, but every 20 pi inches on the surface, JPL for tens of miles. So headquarters was a little bit steamed at us, but they had to admire our cleverness to sneak JPL onto the rover. Next slide, please. So with that background, let's talk about how we get to Mars. And this is about as simple as it gets compared to the trajectories you're looking at to intercept a rogue, interstellar asteroid. This is a piece of cake. So we're looking down on the top of the solar system here. The sun is the yellow dot there in the middle. Earth's nearly circular orbit is outside that. And then finally, we see Mars's slightly elliptical orbit on the outside. So Mars and Earth only line up every 26 months, every 2 years, 2 months. So if you miss your launch window, you have to wait 2 years and 2 months. That's a very scary prospect, and it's happened a couple times to us. So we definitely don't like to do that, because you have to shelve everything for more than 2 years. But assuming you make your launch window, the path out there is half of an ellipse, and we call this a Hohmann transfer ellipse, and it's the minimum energy way to get from Earth to Mars. Another way to put that is, for a given launch vehicle, you get the biggest amount of mass at Mars. In other words, the most science instruments that you can squeeze on a spacecraft. So that's kind of a typical way we go there. We do what's called TCMs along the way, trajectory correction maneuvers. And these are rocket burns to refine the trajectory. Basically, the launch vehicle and the upper stages put you essentially on the way to Mars. So we only use those little TCM 1 through 6 for fine correction of the trajectory. Otherwise, we're just floating in space. We're just like the planets going around the sun. Isaac Newton would, we're coasting, basically. We're not firing the thrusters all the time. If you're a golf fan, this is 352 million mile, or about a 500 million kilometer par 6 golf hole. Every mission I've worked on, we've got at least an eagle, which is 2 under par. That means we canceled TCM 5 and TCM 6. On Perseverance, we actually canceled, I think, TCM 4 also, which is that's called an albatross, 3 under par. That's incredibly rare. So we had a very good launch vehicle injection, and this is the way we get out to the planets. Total trip time here is about 6 to 9 months. Total distance traveled is this 350 million miles, or 500 million kilometers. If you want to send humans to Mars, though, that's your minimum energy path. Call it 9 months. And then it's 9 months to come home. But you actually have to wait on Mars another 1.5 years until Earth and Mars line up again. So it's a commitment for a human astronaut round trip to Mars without, using more exotic propulsion, doing shorter trip time, would be 3 years. 9 months out, 9 months back, and 18 months on the surface of Mars. So, hug your family tight. You wouldn't see them for a little while here. Next slide, please. Okay, so that's how things are in a simple world. My first mission at JPL was not so simple. And this is a Galileo mission to Jupiter, the first orbiter at Jupiter. And in this incredibly strange, bizarre cosmic twist of planetary science, we used all our launch energy on the Space Shuttle Atlantis, October of 1989, when we launched, and we essentially launched backwards. So we went the opposite direction that the Earth travels around the sun. And the reason is we had to kill some speed so that Galileo would fall in towards the sun and fly by Venus. So I think I see, let's look at the diagram a bit first. On the right is Jupiter, the satellites, the 4 large Galilean moons, the things that we saw once we were at Jupiter. But before we get there, we had to do what's called a Vega trajectory, Venus, Earth, Earth, gravity assist trajectory. So the sun is in the middle again. Venus's circular orbit is the next one out, and then the next circle out from that is Earth. Fantastic work on the cursor there. Thank you much. Outside of that, is the asteroid belt, that smeary looking region. That's exactly right, between Mars and Jupiter. And then Jupiter is the outer circular orbit. So again, in this totally crazy world of orbital mechanics, we launched backwards. We used all our launch energy to slow down, and that flew us in by Venus that we see over on the left side. We got a little energy from Venus that put us on the red path going counterclockwise outside the Earth's orbit, back in by the Earth, and we did what's called the Earth 1 swing by 1990. That gave us enough energy to get to the inner edge of the asteroid belt. So then we flew by an asteroid called Gaspra, first ever reconnaissance of a main belt asteroid. That was exciting. But we still didn't have enough energy to get to Jupiter. So we came screaming back by the Earth again, December 1992. And then finally, that's like launch, because we get enough energy from the Earth to fling us on this outer trajectory through the asteroid belt yet again, where we went by the asteroid Ida, the second main belt asteroid visited, and it had a little moon, just like the Morphus and the DART mission. I forgot the name of the little satellite that was hit just last week. But this was a first discovery. We speculated asteroids might have moons, but Galileo actually discovered that back in 1993. Then we slow down, thanks to good old Isaac Newton, but we thought we had one quiet year to catch our breath on this mission. It was not meant to be, because a comet got too close to Jupiter. When will they ever learn? Jupiter's gravity tore it asunder into a bunch of pieces, and these comet fragments then impacted Jupiter. And it was kind of on the backside of Jupiter, as seen by the Earth and Hubble and all the telescopes here. But Galileo had a little more of a front row seat, so we could actually see the impacts directly and then figure out the timing to help Earth observations for that comet Shoemaker-Levy 9 crashing into Jupiter and being destroyed. 1995, we finally arrived at Jupiter, slammed on the brakes, and then spent 8 years out at Jupiter, flying by the 4 moons we see on the lower right. And then each of those moons' gravity was used to change the path around Jupiter to fly by more of those moons. And a beautiful cosmic orbital ballet, and a great introduction to my career at JPL. Next slide, please. So since that worked so well, let's try it on the Cassini mission to Saturn, which would end up then being the first Saturn orbiter. And I'm sorry, it's kind of squished and it's sideways here, and the sun is blue now for some reason, but we see the blue dot there over on the left. Venus's orbit is the first circle outside, and then Earth's orbit of Jupiter and Saturn are labeled as well. And again, in this very strange cosmic twist, we launched backwards so we could launch October 15th of 97. And then I guess that means we are 25th anniversary of launch coming up in about a week and a half. Wow. Hopefully we'll celebrate here. Anyway, we flew by Venus, and this was a V-Vegca trajectory. It's kind of a clunky acronym, but Venus, Earth, Jupiter, gravity assist. So we flew by Venus 1, stole a little energy that put us on that second red ellipse that went outside the Earth's orbit again. We did a deep space maneuver there, a big plane change maneuver, and I understand you have to do that for your rogue asteroid as well. So we did it out there at Periapsis. That made most sense for us. Did another very fast Venus flyby, and a mere 7 weeks later, we came screaming by the Earth for the Earth swing by in August of 1989, finally giving us the orbital energy needed to get out to Jupiter, but still not to Saturn. But we timed it right so that Jupiter would be there when we flew by Jupiter's orbit, got some energy from Jupiter, and then another 3.5 long years out to Saturn arrival, where we slammed on the brakes and then spent 13 years orbiting Saturn. And the Saturn year is about 29 years long. So we orbited for almost half of a Saturn year. In other words, Saturn was clear on the other side of the sun by the time we plunged Cassini into Saturn. Amazingly complex but beautiful orbital dynamics going on here. Next slide, please. So I've talked about this gravity assist a lot, and I think we have some high school students on tonight. And if you're in middle school, just be patient. In a couple of years, you'll take a class called trigonometry, and you'll study something called the law of cosines. And then you might ask your teacher, where is this ever used in real life? And your teacher might not know. And my trig teacher didn't know. And so after I started working at NASA, I showed her this slide, and now she teaches this in high school as a practical application for the law of cosines. So here's how to think of a gravity assist. It's a little complicated, so come along the journey with me here. The spacecraft in this case is moving from the bottom of the page to the upper left. Let's say it's flying by a Jupiter-type planet. Now, with respect to Jupiter, when it's very close to Jupiter, the speed coming in and the speed going out is the same. It's a hyperbola, but the trajectory is bent thanks to Jupiter's gravity. And so from Jupiter's point of view, the sun doesn't even exist there, and it's just this hyperbolic orbit. But what the spacecraft doesn't care about Jupiter's, the speed with respect to Jupiter. Jupiter's just a little gas station along the way, if you will. What matters to the spacecraft is the speed with respect to the sun. So the speed with respect to the sun, when you study vectors, the sum of two vectors. And in fact, the speed with respect of the spacecraft with respect to the planet is the black vectors, the black arrows. Notice how it's the same length, but just rotated to the side there. Now, the speed of the planet with respect to the sun is the gold arrow, and that does not change before or after the flyby. But you have to add those two vectors together, head to tail, and the resultant vector is the blue vector. That is the speed of the spacecraft with respect to the sun. So let's look what happened here. The direction changed. The blue arrow is pointing a different direction, but look, it's longer because it was a kind of a right angle coming in, and it's a bigger than a right angle. And you actually use the law of cosines to figure out what that angle is and how much, the other side, how much your speed increased. So it's amazing. Now, it seems once you have high school physics, you're going to learn about conservation of energy, and nature doesn't give you a free lunch. So energy seems like it should be conserved, but this seems too good to be true. You fly by a planet, you speed up thousands of miles per hour or kilometers per hour. How do you do this? Is energy conserved? Well, energy is conserved, and don't tell anyone. We actually slow the planets down when we fly by them, including the Earth, right? Because I mentioned, Galileo flew by Earth twice and Cassini once. So, oopsie. Hopefully, no environmental impact statement required. I know in Voyager's case at Jupiter, we slowed down the spacecraft, I think, by 1 foot every trillion years or something in its orbit around the sun. So, I think Jupiter won't notice. It took one for the team there, but it did the trick for these gravity assists. So once you hit, some of you may be in trig class and know the law of cosines, you can see directly how you would apply it here. For those of you not yet to see it, when you get the law of cosines, remember back to good old gravity assists. Next slide, please. Now, once we were at Saturn, in Cassini's case, these are more art than science, although there's a tremendous amount of orbital mechanics and science going on here. I want you to appreciate the cosmic ballet, the pirouetting that we did in our prime mission at Saturn, 4 years orbiting Saturn. So what I've shown here is looking down on the North Pole of Saturn on the left, and some of the orbits of some of the moons are shown in red. But those gray ellipses are all Cassini's orbit around Saturn. And look at the beautiful different size and orientations of these ellipses with Saturn at one focus always. But this allowed us to sample the whole Saturnian system, fly by the icy moons, sample the magnetic field in different directions. And we didn't just stay in that plane. On the right is a view, kind of the side view. And you can see some of these orbits were almost polar orbits of Saturn, where you could look down on the North Pole and see the rings like a bullseye. So that's exciting too for the ring scientists. What a gorgeous set of pedal plots we call these orbital tours here. So that's the prime mission. Next slide, please. And then we did a 2-year, what we called an Equinox mission, because as seen from the Earth and the Sun, Saturn's rings went edge on. So they like if you can see the rings tilted this way or this way, but when they're edge on, they kind of disappear. So you can look for shadows in the rings and discover new moons. And this happened in 2009. So we got an extended mission to study this. And Saturn is shown there in the center. And this is kind of a 3D plot, but we had blue orbits. The dark blue are high inclination. A pi transfer orbit is the cyan color. We actually flipped the orbit over in a way. And then the green orbits were for viewing the equinox. Notice those are high inclination as well. And then the orange orbits were flybys of different icy moons of Saturn. And an absolutely gorgeous way to see this whole Saturn system through a unique geometry. But we weren't done yet. Now, at the end of 2008 was end of prime mission. I'm the propulsion guy. I'm an optimist, so I say the gas tank is 10% full, but that really means it's 90% empty. Now, after these 2 years here, first extended mission, we had 5% of the propellant left, so 95% empty. And we said, what do you want to do, scientists, for the next year or two? And they're like, oh, no, we want to go another 7 years. We said, are you crazy? We have 5% of the fuel left. And why do you all agree? You never agree on anything, all the different science teams. Well, another 7 years is another Saturn season, right? Because the Saturn year is 29 years, so each season's about 7 years. And that way we could go from Northern Hemisphere winter to Northern Hemisphere summer during the entire mission and see it basically through the whole seasons, because going from winter to summer is like from summer to winter backwards. So as long as you can get half of the Saturnian year, you've seen it through the whole paces. So then the trick was figuring out how to make 5% of the propellant last for 7 years. And we found a way. Next slide, please. And this is the gorgeous set of orbits over the years 2010 to 2017. So we had highly inclined orbits, equatorial orbits, another set of highly inclined orbits in pink color, the equatorial orbits in orange, another set of high inclination orbits. And then the proximal orbits, if you look carefully there, we're actually flying between Saturn and its rings. And that's crazy, but it actually worked. By the way, by the very end of the mission, I can confidently say we had 1% of the propellant left, plus or minus 2%. So I'll let you think about that. That means we could have run out in the last year or two very easily. And I'm really glad that didn't happen on my watch. There is no gas gauge on Cassini. I was the gas gauge, because your gas gauge in your car is a fill sensor that measures the height of gasoline or petrol at a certain level in the tank. But that doesn't work in zero G. The propellant floats around the tank, clings to the walls. So you need a human gas gauge. And I did my best, but I have uncertainties. And by the end of the mission, my uncertainties were larger than how much we had left, which was very scary. Speaking of proximal orbits, I want to zoom in now on the next slide, because this was a heck of a way to end the mission, the last, let's call it 8 to 10 months. So we did a bunch of F-ring orbits in green. Look how close those are nearly polar orbits, but look how close we're getting to the outer edge of Saturn's kinky braided F-ring. So when we came in there by Saturn, we got amazing, beautiful photos and details there. As wonderful as that was, we even found a way to jump the gap, because you have to do it in one orbit. You can't just kind of slowly cruise through the rings. The ring particles will kill the spacecraft. So in one orbit, we had to jump from F-ring orbits to the proximal orbits. And those were about 6.5 days in length. We did 22 of them. Notice it's a long elliptical orbit, nearly polar, but at Parachrone, the closest point to Saturn, we are coming in between the ball of Saturn and the rings themselves. Crazy. And it turns out that that area is very devoid of particles, thankfully, or it would have killed us as well. But we did all of those, and then eventually we flew by Titan one last time on that red orbit, the impacting orbit. Cassini was a victim of its own scientific successes at Saturn. We found a moon called Enceladus, a tenth the size of our moon, tiny little ice ball that by all means should be geologically dead, boring, unchanged in the 4.5 billion years of the solar system's history. But it is not. It is active water geysers and a subsurface water ocean with hydrothermal vents, like black smokers, maybe, like we see on the Earth, the very place where life might have started on Earth. So we could not risk Cassini running out of fuel, crashing into that beautiful moon Enceladus out at Saturn. So Cassini had to take one for the team and plan its own demise, burn up in the Saturn's atmosphere, so it wouldn't accidentally contaminate these moons of Saturn, particularly Enceladus, with bacterial spores from Earth. So it made for a sad day for us 5 years ago, but we were almost out of funding, some radiation damage. We're definitely almost out of propellant, so it was time to end the mission in a clean kind of way. Be good stewards of the Earth and of the solar system. Dispose of your trash. Forgive me for Cassini for calling you trash. Next slide, please. Okay, so that everything we've done so far talked about, you launch, you do like an ejection burn, and then you coast. And there's something aesthetically unpleasing about that, right? If you're coasting, that takes time. How about you thrust the whole way? Well, you can't really do that with chemical rockets. You'd run out of fuel very quickly. So I worked on a mission called Dawn, and this was NASA's first science mission to use what's called electric propulsion. And this is much different kind of scenario. So we see the sun here, yellow ball surrounded by orange. Then the Earth's orbit is in the green there. Notice we didn't, this is a very weird, different looking trajectory. We spiral out slowly like a spirograph. And in fact, where you see the little blue periods is when the ion engine's thrusting, because it's a xenon thruster that has this blue-green glow coming out the back of the engine. And so we coast thrust, and that gradually builds up speed. And notice then we crank around to a Mars gravity assist in February 2009. We coast a while, start thrusting again. That spirals us out into the asteroid belt, and we arrive at the asteroid called Vesta in July of 2011. Vesta's the second biggest main belt asteroid. But since we've matched its orbit, we can actually kind of sneakily just, capture into orbit around Vesta, lower the orbit, do mapping for a year while Vesta goes around the sun. That's already, maybe you could get a chemical propulsion mission to do this part of the mission, maybe. But you'd never be able to leave Vesta. We then fired up the engine again, spiraled out further to the outer edge of the asteroid belt, and met up with Ceres, the biggest main belt asteroid, March of 2015. And that's at the very bottom of your plot. And Ceres is shown there on the left, including that bright spot that we thought was the water ice and maybe more like Epsom salts. And then we captured into orbit around Ceres till the end of the mission, some 3.5 years later, and did various orbits at Ceres. But you would never be able to pull this mission off with chemical propulsion. Ion propulsion now the thrust of an ion engine, even though an ion engine's this big, the thrust coming out the back is the same as the weight of a piece of paper in your hand. So it's incredibly low thrust. It literally would suck as a launch vehicle. It's a vacuum cleaner on Earth. But in the vacuum of space, 0 to 60 miles an hour in 4 days, acceleration with patience, and it uses 10 times less rocket fuel than chemical rockets. So if you have weeks, months, years to fire an engine, it's a much more efficient way to get around the solar system, particularly if you have multiple targets like we had here with the Ion mission of Dawn. Next slide, please. Okay, now speaking back to a chemical mission, but I have to talk about Voyager. I'm working Voyager, and Voyager took advantage of a incredibly, truly rare cosmic alignment of the outer planets. In the 1960s, someone figured out that all 4 gas giant outer planets, Jupiter, Saturn, Uranus, and Neptune, would be on the same side of the sun. And you could send one mission, in theory, to visit all 4 of those planets. And in fact, you could get to Neptune within about 12 years. Remember the Hohmann transfer ellipse I talked about at Mars? A Hohmann transfer ellipse to Neptune takes 30 years. So it's way longer than any presidential term or congressional term, or you can't torture a PhD student for 30 years. So if you could get there in 12 and get Jupiter, Saturn, Uranus, and Neptune within a dozen years, that's amazing. The bad news is this alignment only happens every 176 years. So they went to Richard Nixon, president of the US in the early 70s, and said, now look, in 1977, Jupiter, Saturn, Uranus, and Neptune are lining up on the same side of the sun. And this only happens every 176 years. So the last time it happened was 1801, and Jefferson blew it. Don't make the same mistake. So to Nixon's credit, he said, let's do 2. So he got Voyager 1 and Voyager 2 funded. We launched there in 1977, 45 years ago, last month. Now, it drove the press crazy. Voyager 1's in blue, Voyager 2 is in red. And Voyager 2 launched first. And the reporters could just never understand this. But we didn't want to confuse them later because Voyager 1 was faster. So it passed Voyager 2 and got to Jupiter and Saturn first. So we figured it was better to confuse them at launch than for the whole mission. Notice the launch there, 20th of August, 1977 was Voyager 2. And we launched out from Earth directly to Jupiter. And Voyager 1 was a couple weeks later. We got to Jupiter about 2 years later, 1.5 years later. And then there was an attempt then to go on to Saturn by using Jupiter's gravity assist, kind of like the gravity assist example I showed you. And indeed, that worked fine. And we ended up at Saturn in November of 1980 for Voyager 1 and August of 1981 for Voyager 2. Now look at Voyager did a strange turn above the plane of the planets called the ecliptic at Saturn. And that was absolutely on purpose. Voyager 1 was targeted to Saturn's large moon Titan second biggest moon in the solar system, only moon with an atmosphere. And Titan was so interesting that we planned Voyager 1 to fly by that moon at the expense of getting to Uranus and Neptune. And in fact, if Voyager 1 would have failed at Titan, then we would have reprogrammed Voyager 2 to go by Titan, and that would have precluded it from heading on to Uranus and Neptune. And we still might not have had a spacecraft go by those two planets, because here in 2022, still the only spacecraft to ever go by Uranus and Neptune was Voyager 2. But luckily, Voyager 1 did its work at Titan. Voyager 2 was given the go-ahead to fly by Saturn in such a way that gravity was bent to head to Uranus in January of 1986, bend the path slightly, then to get to Neptune in August of 1989. Now notice, after Neptune, Voyager 2 took a dive south. So it flew over the North Pole of Neptune, which was required to fly by Neptune's very interesting moon, Triton, which orbits Neptune backwards and looks a lot like Pluto. Triton, it turns out, was fascinating. It has active nitrogen geysers, even though it's barely above absolute zero. So that's crazy. But thankfully, Voyager was able to take advantage of this incredibly rare cosmic alignment. Next slide, please. And how do we talk to all these spacecraft? Well, we have deep space network antennas around the world in Goldstone, California, outside of Madrid, Spain. And for our Aussie viewers today, outside in Tidbinbilla, outside of Canberra in Australia. So thank you for your service, especially for Voyager 2. Because as I showed you, Voyager 2 is so far south of the ecliptic plane that without your help in Australia, we would not be able to track Voyager 2 and send it commands. So thank you very much. Next slide, please. Okay, now the Voyagers are still going, and the signal to get to Voyager 1 takes 22 hours to get there and 22 hours back, almost one light day away from Earth. But remember, the nearest star is 4 light years. We've traveled 45 years and we're not even 1 light day away. So to make ourselves feel better about our lack of progress, we put everything on what's called semi-logarithmic scale. So the sun is there. Earth's at 1 astronomical unit by definition. An AU is about 93 million miles or 150 million kilometers. So Saturn's 10 AU, 10 times further away from the sun. And then out to 100 AU is the edge of the sun's influence called the heliosphere. And the Voyager penetrated that bubble and is in interstellar space, both Voyager 1 and Voyager 2. And so we're in 100, 150 AU kind of range from the sun. Then nothing really much happens till about 1,000 AU, and that's when the Oort cloud kicks in until about 100,000 AU, and then some stars start appearing outside of that. So Voyager will fly by another star within a light year or so, but you got to wait 40,000 years. So people are going to have to wait a long time for the gold record to hear the sounds, pictures, languages, and greetings from planet Earth. Next slide, please. Okay, I'm running a little low on time, not surprisingly, so let's get on to it's a much smaller portion of my talk. We want to talk about remote sensing and how to measurements. How do you do science measurements once you've taken this beautiful spacecraft there and figured out your orbital mechanics? So there's 2 kinds of flavors of instrument. I want to get you a sense here from Cassini. There's remote sensing versus what we call in situ, which is a Latin term, means in the situation or right there. So remote sensing means you're looking at something at a distance. Infrared cameras, ultraviolet cameras, visible light. You're measuring light reflected off a distant object. You don't need to be right in its face to get the data. Webb telescope's an example of that for sure, remote sensing. Now, in situ means you're actually sampling directly something right around you. So like dust hitting the spacecraft, the magnetic field there, plasma waves, sniffing the atmosphere of Saturn or Enceladus, this moon, with INEMS, ion and neutral mass spectrometer. So you think of one like the cameras and the other kind of like the fields and particles instruments and sensors, then you're close. Next slide, please. Okay, so how do you decide what to look at and what wavelengths and all these things? So you may study this if you haven't yet, and for sure in high school physics, the beautiful thing called the electromagnetic spectrum. So radio waves are on there, visible light's on there, but a whole lot of other stuff is too. So you can look at it across the bottom is increasing frequency and decreasing wavelength. So radio waves are there first, and then microwaves, into the infrared, the ultraviolet. In between those is a little narrow band of visible light, the colors of the rainbow there. Beyond the ultraviolet are X-rays and gamma rays, more high energy particle events. So the stuff to the other side of ultraviolet tends to not ionize things, but when you have higher energy, you can actually ionize stuff with gamma rays and X-rays. So this is, and the reason this is important is different objects emit or reflect in different places along this continuum here. And in fact, they're, depending on what chemicals are there, they can have absorption bands. So you see dark lines in the spectrum or the rainbow that tell you what chemicals are there. So you can do all kinds of really cool stuff by understanding this electromagnetic spectrum. Next slide, please. And as an example, so what can you get from remote sensing? So now this is looking across that same wavelength band, a little tighter here, 100 nanometers up to, let's say, over 10 centimeters. So this goes from ultraviolet to visible light to infrared to microwaves. And things that you can do with active sensors, which means you kind of, like radar is an active sensor. You bounce a radio wave or a microwave off of a surface and measure the reflected signal and figure out what it's made of. And there are all kinds of bands there, Ka, Ku, K, X band, C band, S band, L band. Laser fluorescensors are another type. Now, passive sensors are a little different. There you're just measuring the inherent brightness of a body, like thermal infrared's a classic example. Night vision goggles. You don't have to ping somebody. They give off a heat signature with your thermal infrared sensors, your night vision goggles. You can see them and find them. So those are more passive sensors. And I mentioned this earlier, you can get chemical information from the absorption of certain wavelengths, dark lines in the rainbows. And this is in visible light, infrared, ultraviolet. The temperature, room temperature stuff emits in the infrared. You know, stars emit a lot in, like our sun emits mostly in visible light, which is, convenient for us for driving solar panels, stuff like that. High energy materials they radiate more in the X-rays and gamma rays, black holes and crashes and galactic mergers and stuff like that. So it's kind of cool to look across the spectrum and think of the different ways you can measure these phenomena. I'm about done. Let's head to the next slide, please. So this is a real picture that Cassini took during its 13 years in orbit around Saturn. And we can't point the Cassini cameras at the sun because they would fry the cameras. But twice in the mission only, two times in 13 years, the sun was behind Saturn as seen from Cassini. So we could do a long time exposure and take a series of mosaics, about 200 images, about 12 hours of imaging. And we knew Saturn would be lit up in this ghostly backlight of the sun behind Saturn. And we knew it'd be beautiful, but not this beautiful. It just absolutely blew our socks off. And we see things like refraction, the light bending around, showing us the rings on the dark side of Saturn there. We discovered some new rings and some new moons when we did this. We see the gorgeous E-ring, which is a set of material that is put out by Enceladus, this active geyser moon of Saturn. But I think most poignantly of all, there's one little tiny blue pixel that's pointed out there. It's hard to see, but one pixel across, gorgeous blue color from 900 million miles away, 1.5 billion kilometers. That is us. That is everybody you've ever known. That everybody that's ever lived has lived out their life on that tiny blue marble. It would behoove us to do everything in our power to protect it for the future generations. And when I saw this, I thought of the poet T.S. Eliot, who wrote in The Wasteland. And he had a comment about exploration. And it seemed so perfect for this Cassini image. We shall not cease from exploration. And the end of all our exploring will be to arrive where we started and know the place for the first time. Thank you very much. I'll be happy to take your questions. And Claire, you're muted.
Can you hear me?
5 by 5.
Okay. Claire, can you try talking? Nope. All right. Well, yep. I guess I'm running the show now. All right. So Todd, let me put you here in the hot seat and get you some questions. We've been getting comments from the students as you've been talking. Thank you for that amazing presentation as always. And I love your enthusiasm and excitement for the work that you do. My first question, I love this question from Olivia. What was your inspiration?
Oh, that's such a great question. Thank you, Olivia. I had so many people that inspired me through the years. It was my parents. They were always super supportive with every nerdy science thing. You know, I had a weather kit, electronic kit, a crazy chemistry set. I melted holes in the street in front of their house. I feel really badly about that, but you know, they and my mom got my dad and I a telescope. My grandparents showed me National Geographic magazine for the first time, so I saw the pictures from Voyager at Jupiter and Saturn, and that's what inspired literally my path to JPL. And to think I'm now on that Voyager mission is amazing. But I'm frozen. Okay,
You're good.
hopefully
We can still hear you.
okay, great. That's good. And then I had the best teachers. They were so good. I went to a public school in Wichita, Kansas, and we just happened to have the most amazing math and science teachers in the universe there. And they nurtured every crazy experiment and after school. So I just had a ton of mentors and supporters along the way. So they are the ones. And then of course all the people now that I saw these JPL documentaries, and they were heroes to me. People like Ed Stone, the Voyager project scientist. And now I'm working with them, they're peers. And that is really strange to have this hero worship for people that, you grew up with seeing the documentaries, and now you're on the team with them. It's absolutely amazing.
That is amazing. And shout out to all the teachers who are supporting teams right now, because they are those people that are going to be influencing the next generation that may be your future coworkers.
Absolutely. Can't wait to welcome them aboard.
So we had some great comments while you were presenting. One question to start off was, what is your favorite rover? Can you choose a favorite?
I don't think I can. It's like the favorite children question, because I love Pathfinder because it was first, right? It was so cute, but I didn't work that one. So it would probably not be Pathfinder. But amongst the others, like Spirit and Opportunity were my first ones. So that's special. And then Curiosity was the first with the crazy landing. And I was more heavily involved in that one. But then Perseverance, I was the head propulsion guy for operations. I didn't design it or anything, but I was actually heading up the propulsion team. So I had a lot of pride in that one, let's say, just because I had a little team under me. So for different reasons, they're all incredibly special.
Well, this one might also be difficult to answer. What was the most exciting mission you have ever done?
Yes, thank you, Sayu. That's a tough one too. Galileo was exciting because it was my first one, of course, and then Cassini just with the discoveries. But I think you can't beat the excitement of a Mars landing, because it's like instant payoff. You launch and you're there with between 6 and 9 months later, and to land or not land, and then within 5 minutes you get the first pictures from that part of Mars. But I also worked a mission called Deep Impact, where we crashed into a comet way before DART did it. And that was so cool because we had a mothership that was outside that could watch the crash while the impactor got destroyed by the comet. So to see that explosion, in space, and it was on July 4th of 2005, July 4th, Independence Day in the US. So that one's hard to top for just sheer excitement, because I guess it's the teenage boy in me, like to blow up fireworks and things. And this was just a huge cosmic firework.
That's a great answer. Okay, I like this question. What was the coolest development going from the earlier rovers and landers to the modern ones?
Yeah, that's a great question. Well, the helicopter obviously comes to mind, because we never had that capability before, because the Mars atmosphere is so thin. It's like trying to fly at 30,000 meters or 100,000 feet. A helicopter on Earth, you wouldn't get very far. So we had to make them super lightweight and counter rotating blades spinning really fast, solar powered. So that was a neat technology development for sure. But there's another thing I love called terrain relative navigation. We landed in an area with Perseverance that was so dangerous that Spirit, Opportunity, Pathfinder, or Curiosity could not have landed there. Too many rocks, too many hazards. We actually took pictures during the landing, and then the smarts of the rover computers compared it to a known map from orbit and and did diverts. So it tilted to the side and fired the rockets a little. So it pinpointed a landing site that was safe. And there weren't many safe areas within this landing ellipse. So that was a really cool new technology. It's absolutely going to be needed for human landings on Mars. And eventually, by the way, this rover is collecting samples that we will bring back to Earth. NASA will bring those back as part of Mars sample return campaign. So when we land the Fetch rover or helicopters, they go pick up those samples to blast them into Mars orbit and then back to Earth. We need precision landing again to get close to where those samples are.
It's just wild, this technology that you have to control things so far away. And that's this next question is, what is it like to be able to maneuver the rovers and these spacecraft like from so far away here on Earth? And this is Adrian in Texas.
Yeah, well, Adrian, that's a great question. I mean, to me, it's the honor of my life. Don't tell my bosses I do this job for free, but I have to pay my bills, but I'm just so passionate about it. Since I'm a propulsion person, I actually haven't got to drive the rovers themselves, but that's another whole exciting set of people that get the privilege. They don't care much about getting from Earth to Mars. They just want a safe landing and then start driving the vehicle. So when you do that at JPL, you have to get a Mars driver's license. And it's much harder than a California driver's license. And there's a gender difference. One gender is a little better at rover driving than the other. Ooh, controversy. And I won't make you guess. I'll just tell you, women are a little bit better Mars rover drivers than men are. And someone asked why to students, and they're like, road rage? And I was like, well, no, Mars isn't crowded enough yet to have road rage. I think we're okay. But it's kind of related to that. It's about patience. Because as a man, I can say, ask the young men in the audience, anybody that's driving, who's been stuck before in mud, sand, snow, ice? I've been stuck in all four of those. What does our male brain tell us to do when we get stuck? Just need more gas, hit the gas. And then you make it worse. You dig yourself in a deeper hole. So because of that, we found that the women Mars rover drivers are a little more patient and a little better.
Interesting.
That is really interesting and humbling for you to admit that. So appreciate that.
That's okay. I know my limitations.
So Jackie wants to know, what are you actually working on right now?
Great question, Jackie. So I'm 2/3 on Voyager, which is still going after 45 years. We just celebrated our 45th anniversary. And we have so many problems with this mission because it's ancient, right? 45-year-old spacecraft is geriatric for sure. So trying to keep these things alive. We lose 4 watts a year. The propellant lines are about to freeze. Our brains got a little scrambled earlier in the year. We fixed that problem. So some of the hardest engineering I've done in my whole career, which of course means it's the most fun because we love a challenge as engineers. And that's 2/3 of my time. 1/3 is on an Earth orbital called SMAP. It's Soil Moisture Active Passive. And it's nice to give something back to the Earth because I certainly don't have the best carbon footprint. So this is a way to help out, hug the planet a little bit. And what we do is we measure the moisture in the top 1 meter of soil all over the Earth every 8 days. So we can do things like drought prediction, flood risk assessment, optimal planting times for crops, tracking mosquito-borne disease. It's even helping with climate weather forecasting, and even for my home state of Kansas, tornado prediction, because it turns out soil moisture might correlate with whether tornadoes form or not. So it's very exciting to give a little something back to the Earth with that mission.
Wow,
Yeah,
that's really amazing.
All right, I have one more question here from the pre-submitted, and this is more of a physics question. What's your opinion on wormholes? Do you think they're real?
Ivan, that's a good one. Yeah, I don't know. It's they're certainly convenient for science fiction writers because, as you saw with my Voyager plot, right? If to get anywhere, Voyager's going pretty fast, like 34 to 38,000 miles an hour, and yet after 45 years, we're not even one light day from Earth, but the nearest star is 4 light years. So I think it's possible. The one area where you might think it's possible, you can't see inside a black hole, because even if you were in a black hole shining a flashlight, not even light can escape, because the gravity is so massive near, inside the event horizon that the escape velocity is higher than the speed of light. So since nothing can go faster than the speed of light, you can't see inside there. So it's kind of speculation. What would be, does that connect to something? So it's kind of a hard question to ask or to answer, because you can't get inside the black hole. But it's probably a good thing, because if you went in feet first, your feet would feel a lot more gravity than your head. And for a nanosecond, you'd be a nice tall NBA player, but it would rip your body to shreds, with more gravity at your feet than your head. So probably better to observe those from a distance.
Yes, that's that spaghettification thing, right?
Yeah, exactly.
Spaghetti. I can't think about that. All right, we've got one other really great question from the live comments. What words of wisdom do you have for students who may be struggling in maths or just generally finding things tough?
Well, and it sounds like a cliche, but literally don't give up. Because as you kind of tell, JPL was my dream job since childhood. Saw those pictures, National Geographic. I got rejected twice by JPL, as a sophomore in college, and then right after my bachelor's degree as well. So I kept business cards, and I was persistent, because I knew once I got in and could shine and follow my passion, that they would not regret that decision. So you got to look at all of those things as just temporary obstacles. Whatever that path and dream is, get people to help you along the way to clear that path, but blaze a big trail for yourself, and don't take no for an answer.
Oh, that's great advice. So I always end with this, and this is a great segue. Do you have any other advice or encouragement for those who are listening as they pursue their goals?
I do, because I like to think that there are many ways to answer some big questions that humanity's had for thousands of years. And we are so privileged. We live at a time when STEM can answer those questions: science, technology, engineering, and mathematics. And so these are the questions I get to help answer every day. And don't blurt out the answers. They're kind of rhetorical questions. But if these questions interest you, then a STEM career, a NASA career, your own country's space agencies, these might be places to seek a career. And here's the questions I get to help answer every day. How old is the universe? What is the fate of the universe? Will it collapse on itself or continue to expand forever? Why in 2022 don't we know what 95% of the universe is made of? We call it dark matter and dark energy, but that just reflects our ignorance. We don't know what's there. That's pretty embarrassing. We've been studying this stuff a long time. Why don't we know what 95% of the universe is? How did life form on Earth? Is life unique to Earth? Is there single-celled organisms that formed in our solar system? Is there intelligent life that formed in other solar systems? Will we ever make contact with them? If so, how do we have a conversation? How do we get to these worlds that seem so infinitely far away? Once we talk to these worlds, let's ask them the big questions. Have they cured their diseases? Have they learned how to get along with each other so that they haven't destroyed their own planet? Are we destroying our home planet so that our kids and grandkids can't live here anymore? So if these questions interest you, please consider careers in your local space agency, other STEM careers. There's no shortage of problems to tackle here in 2022, and can't wait to have you aboard to join in this STEM journey for your careers. Thank you.
Oh, that's so exciting. Thank you so much, Mr. Barber, for joining us and those words of wisdom. What an inspiration your story is, and we wish you the best of luck as you continue in your journey as well.
Thank you very much, Claire and Natasha. I really appreciate you hosting tonight, and just delighted to share in the students' triumphs and their struggles in space teams. You'll get through it. It's going to be great.
Absolutely. All right. Well, we will see everybody back here tomorrow for the kickoff for day 4. Have a good night.
Good luck, everyone.
Bye-bye.